Welcome back. In this video lecture, we will continue our discussion of main group elements. We will cover everything from group 2 all the way to group 18. The relevant reading materials are in chapter 8. Now, when using this video lecture, I would suggest you take this as a guide for reading chapter 8 instead of relying solely on the content of this PowerPoint presentation. Group 2 elements include beryllium, magnesium, calcium, strontium, barium. They are commonly referred to as alkaline earth metals. And just as a side note, group 1 metals, lithium, sodium, potassium, etc., are commonly referred to as alkaline metals. Now, in this list of elements, beryllium is very different from the rest of the four. Beryllium is much less metallic, especially in its compounds. There's a lot of covalent behavior that you do not see in the rest of the elements. The chemistry of this group 2 elements is relatively boring. Okay, the most important reactions are basically two. One is the reaction of magnesium, calcium, strontium, barium with water, and that produces the corresponding hydroxide and hydrogen. The reactivity of magnesium is relatively low, but for calcium and the rest of elements, they all react violently with water. For magnesium, there's another important reaction that is the formation of Grignard reagent. That is the reaction between alkyl halide with magnesium powder. Grignard reagent is a very popular starting material in organic synthesis. It's a powerful nucleophile. The other important chemical in this group is beryllium dichloride. It's a very interesting compound in terms of its chemical structure. So if you think about the valence shell structure of beryllium, you will realize that it only has 2 electrons. And in beryllium dichloride, after forming the 2 bonds with chlorine, it only get to 4 electrons. So that's still far away from 8. So in order to fulfill the octet rule, in the solid state, each beryllium forms 2 additional bonds with the nearby chlorine atoms. So instead of having a linear structure, beryllium dichloride actually takes more like a tetrahedron type of structure for the beryllium. All right, going to group 13. This is boron, aluminum, gallium, indium, and thallium. In this group, again, there are 2 distinct parties. Boron is non-metallic, and the rest of the elements are metallic in nature. The important and interesting chemical facts here are the bonding of boron. We learned about boron trifluoride and boron trichloride, and we know those are important Lewis acids. And this Lewis acidity is due to the particular valence shell electron configuration of boron. It only has 3 electrons, and after forming 3 bonds, it still cannot fulfill its octet rule, so it tends to accept other electron pairs, so that make them Lewis acids. In the absence of Lewis bases, certain boron compounds also find lone pairs among themselves. So the primary example in this scenario is diboron. So if you think about BH3 boron, boron has the same kind of problem as BF3. So it does not have 8 electrons on the boron atom. So the way it solves the problem is to dimerize. Now in this diboron structure, you'll find each boron atom forms a tetrahedron type of structure, and there are two hydrogen atoms in the middle that forms two covalent bonds with two boron atoms. Now this is a structure that cannot be explained. That cannot be explained by Lewis-Dot structure. If you think about the bonding situation of hydrogen atoms in the middle, it only has one electron but forms two covalent bonds. Okay, but in the framework of molecular orbital structure, molecular orbital theory, this is not a problem. This is basically a so-called three-center, two-electron bonds. Another interesting boron-containing compound is the borazine, shown here. It mimics the structure of benzene, basically, but instead of having a six-membered carbon ring, here you have boron, nitrogen, alternating configuration. Now, nitrogen has five valence shell electrons, and boron has only three. But these two together can make eight. So in this structure, boron and nitrogen forms covalent single bond, and then when this remaining lone pair on nitrogen is shared with the boron, because boron has an empty p orbital in this case, and that forms a conjugated pi system very similar to that of benzene. All right, going down, there are other interesting facts about the elements of group 13, gallium and indium. Those two are interesting low melting point metals. Gallium has a melting point of around 30 degrees Celsius. Indium has a melting point of around 156, I believe. And both have been used quite often in making low melting point alloys. Finally, I want to make a comment on the chemical properties of aluminum. Aluminum is an important structure material. There are a lot of aluminum alloys used in making airplanes, and now actually making Ford trucks. Some of the newer F-150 trucks are made of aluminum instead of using steel. Aluminum is a low density metal. It's actually highly reactive, but aluminum alloys do not give us the impression that it reacts with oxygen and water during their use. And the reason being, there's a thin layer of aluminum oxide that forms on the surface, and that thin oxide, only a couple of nanometer thick, protects the underlying metal from reacting with air and water. However, if you can get rid of that layer of thin aluminum oxide, then aluminum can even react with water to produce aluminum oxide and hydrogen gas. So in this regard, it's pretty similar to lithium, sodium, and magnesium. And the only difference is in the alkaline metal and the alkaline earth metal cases, those metals do not form a dense layer of aluminum oxide, but aluminum can. Okay. So I want to leave this as an exercise for you, and I want you to find out how you can prevent and interfere with the formation of aluminum oxide layer on the surface, such that aluminum can react with water to produce hydrogen. All right, going to group 14, this is carbon, silicon, germanium, tin, and lead. In this group, there's a very clear trend starting from, so going from top to down, you have diamond, which is one particular form of carbon. Diamond is a high band gap semiconductor. If you go down to silicon, the band gap drops significantly to about 1 electron volt, and germanium has an even smaller band gap. Going down to tin and lead, both become metal, and this is a recurring trend in other columns. That is, if you go from top to down, the metallic behavior generally increase. The most important element in this column is carbon. Carbon is probably one of the most elements in chemistry. Carbon has many different allotropes. Diamond and graphite has long been known, and fullerenes such as carbon-60 was discovered in the 1980s. Now, if you read the text, you'll find other interesting allotropes of carbon. For example, the recently discovered graphene that won a Nobel Prize in 2014. In the term paper topics, you'll find a couple of those papers related to the study of graphene. There are interesting isotopes of carbon. There are 3 isotopes of carbon. Carbon-12 is the most abundant form of carbon. Carbon-13 is much less abundant, but is NMR active. And then there's carbon-14, which is the least abundant. It's produced by cosmetic rays striking the atmosphere with the nitrogen atoms that produce radioactive carbon-14. It has a half-life of around 5,700 years. Carbon-14 is involved in the so-called carbon dating process. The idea behind this is pretty simple. All living forms, animal or plant, have to take in carbon in one form or the other. Now, this carbon will include a tiny amount of carbon-14 that is produced by this cosmetic ray process. Now, once the animal or plant dies, then they will no longer take in additional carbon-14. So the amount of carbon-14 in those materials, in those human remains or plant remains, will only decrease through this radioactive decay. Now, once you know the concentration of carbon-14 in the remain, you can calculate based on the half-life how much time has passed since the death of this plant material or animal material. All right, important compounds in this group, again, is centered around carbon. Carbon monoxide is a very important ligand. Carbon dioxide is produced by the burning of fossil fuels and many other processes. It's one of the most important greenhouse gas that is responsible for the increase of global temperature. For silicon, there's a silicon dioxide. Basically, this is quartz or sand. And then there's a glass. And I want to emphasize here that glass is not silicon dioxide. Glass is silicate. And depending on the type of glass we're talking about, the cations can be very different. The common window glass has a lot of sodium and calcium in it. Now we go to group 15, nitrogen, phosphorus, arsenic, antimony, and bismuth. In this column, you again see this behavior that we discussed before. That is, if you go down the periodic table, the metallic behavior of the elements will increase. Nitrogen is an insulator. Phosphorus, depending on its form, can be either an insulator or a semiconductor. Arsenic is a semiconductor. Antimony and bismuth are metals. The most interesting elemental form of this group is P4, which is white phosphorus. Phosphorus has 3 important allotropes. White phosphorus, which is molecular, P4. In this form, it has 4 phosphorus atoms forming a pyramid-like structure. There's also red phosphorus and black phosphorus. and in both cases, they form extended solid state material. The important compounds in this group mostly are related with nitrogen. So there's ammonia, NH3, azide, N3 minus. Again, this is a linear anion that we discussed before. There are a lot of nitrogen oxides. There's a nitrous oxide, that is N2O, and there's a nitric oxide, NO, nitrogen dioxide, NO2, dinitrogen pentaoxide, N2O5, so a lot of them. Nitrous oxide is commonly known as laughing gas. It is used in dental anesthesia. Nitric oxide, it is prepared in industrial scale by the oxidation of NH3. It is also a common pollutant produced during the combustion of gasoline in internal combustion engine. NO2 can be produced by the direct oxidation of NO with oxygen. It is the direct precursor to the production of nitric acid in industry. The most important phosphorus-containing compound is probably phosphoric acid. It's an important industrial commodity for the production of fertilizers. The most important reactions in this group are all related to the industrial production of chemicals. The first one is the Haber-Bosch process. It is the industrial production of ammonia, NH3, from nitrogen gas and hydrogen gas using an iron catalyst. It is probably one of the most important reactions developed in the 20th century. It is responsible for the production of about 400 to 500 million tons of fertilizers every year. This process uses about 1 to 2% of the energy produced today. The second important reaction or series of reactions is the industrial production of nitric acid from ammonia. This involves a series of reactions. First, the oxidation of ammonia by oxygen using a platinum catalyst, and that process produces nitrogen monoxide or nitric oxide. And this is followed by the oxidation of nitric oxide by oxygen to NO2. And finally, the reaction with between NO2 with water to produce nitric acid and nitric oxide. You should see the text to make sure you understand the whole series of reactions and be able to balance them. And the last reaction is the industrial production of phosphoric acid from phosphate minerals by reaction with sulfuric acid. All right, group 16, that's oxygen, sulfur, selenium, and tellurium. Important elemental forms and compounds in this category is there are oxygen, and then there's ozone. Ozone's Lewis dot structure or resonance structure is an interesting case that you should look into. There's S8, sulfur, unlike oxygen. The most common form is not S2, instead is S8. However, at high temperature, S8 does break down to produce S2, so there's still some similarity between oxygen and sulfur. The most important compounds are all related to sulfur. So there's a sulfite, that's SO3 2 minus, and there's a sulfate, that's SO4 2 minus. And then there's a thiosulfate, which basically is very similar to the structure of sulfate, but having one of its oxygen replaced by sulfur. Sulfite is commonly found in wines. Actually, if you look at a lot of those wine labels, you'll find there's a warning that it contains sulfite. That sulfite is produced by the reaction between sulfur dioxide, which is used as a preservative, with water. Thiosulfate is a common and popular reducing agent used in many applications. The important reactions in this category, the first one is the conversion between ozone to dioxygen catalyzed by chlorine atom. This is the process that is responsible for the depletion of ozone in certain regions of Earth. The second most important reaction is the industrial production of sulfuric acid. This starts with the oxidation of sulfur or metal sulfide to produce sulfur dioxide. That is followed by the further oxidation by oxygen to produce sulfur trioxide. And finally, the reaction between sulfur trioxide and water to produce sulfuric acid. Group 17, fluorine, chlorine, bromine, and iodine. This group is commonly referred to as the halogens. The elemental forms of this group is universally a diatomic molecular form, so F2, Cl2, Br2, and I2. So there's not much to talk about there. There are several important reactions though. The first one is the oxidation of water by F2. So F2 reacts with water to produce oxygen and hydrofluoric acid. This is a very rare case in which oxygen is produced by an oxidation reaction. Fluorine is the only element that is more oxidizing than oxygen. The second reaction concerns the formation of hyperchlorite ClO- from chlorine. This is the reaction between chlorine with sodium hydroxide that produce sodium chloride and sodium hyperchlorite. Sodium hyperchlorite is basically bleach. And finally, there's industrial production of chlorine gas by electrolysis of sodium chloride solution. In this reaction, sodium chloride and water, under the driving force of electricity, produces chlorine gas and sodium hydroxide. And both products, chlorine gas and sodium hydroxide, are industrial commodities. This reaction is not on the text. However, I would like you to do a little bit of your own research and find out the detailed reaction and make sure you understand the process and be able to balance the reaction if needed. All right, finally we come to group 18. This is the noble gas: helium, neon, argon, krypton, xenon, and radon. All these elements exist as a single atomic molecule, so there's not much to talk about their elemental form. However, there are some interesting facts about those elements that I like to mention. Helium, for example, liquid helium has the lowest boiling point of all liquids out there. All those noble gas, when they are excited by electricity, can produce visible emission, and that's the working mechanism of all those neon signs. It actually does use neon, but also many other noble gases. Radon is the heaviest noble gas. It's unlikely to encounter radon in a laboratory setting, but actually radon has a lot of relevance to our day-to-day life, especially in Pittsburgh area. It turns out that radon can be produced by the radioactive decay of radium, which exist in a lot of rocks. So those radon gas will be produced essentially in the Earth's crust. Those radon gas will eventually rise and get released into the atmosphere. Or if you have a basement in your house, they will accumulate in the basement because radon is a really heavy gas. Now, radon is radioactive, so this can become a health hazard because if you inhale radon, those radioactive molecules could damage your lung and increase the chance of getting a lung cancer. So in some situations, it might be necessary to install a radon mitigation system in your basement. This is basically a air fan that pumps gas out of the foundation below the basement. So that will remove radon gas before it has a chance to enter the basement. Chemistry-wise, even though those noble gas were long believed to be inert, it turns out that they can indeed form certain compounds. That is especially true for the case of xenon. In the text, you'll find a long list of chemicals between xenon and oxygen or fluorine. My expectation here is pretty minimal. I'd like you to look at the long table in the text that lists all kinds of structures of xenon-containing compounds. My expectation is you understand the bonding of those compounds in terms of VSEPR theory and be able to make correct predictions of their 3D geometry. All right, so this will conclude our discussion today. As I said at the beginning, I'd like you to use this presentation as a study guide. And you may notice that I did not list all the exact chemical reactions out there, but I simply tell you what those reactions are. So for example, the industrial production of nitric acid, you should look at the text and make sure you understand what those reactions are and be able to balance them. This chapter also introduces a lot of new compounds and chemical reactions. It's not realistic to remember all of them, but rather I'd like you to develop a sense of the chemical reactivity of those elements. Think about the periodic trends, think about how oxidizing they are, how reducing they are, and if you know one element very well, you can extrapolate the property to the nearby neighbors. All right, so that will be the end of the discussion today, and we'll see each other again on Wednesday. Thank you.